Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering. We will continue our discussion on the description of strain, what we have just looked at yesterday. I will quickly review what we have just started with. So this is exactly what I have shown in the slide. We have just gone through. Similar to stress, whatever the description we have seen, we are going to see the similar kind of a description, a strain at a point. This is what I just started yesterday. And we went through some normal classification of the strains, and then we also looked at what is a normal strain and shear strain, and it is exactly the similar terminology as we have seen in stress, normal stress, and here it is normal strain, shear stress and shear strain. Similar geometrical conditions will be considered here as well. So I will quickly skip this slides because we have already gone through this. And one point I just want to mention here is before we get into the details of this normal and shear strain, there is another term we have seen that's called volumetric strain, which is denoted as E, small e, which is a change in volume divided by original volume. And this volumetric strain is also simply related to normal strain, and that is exactly I have stopped yesterday, and then we will just see from that point. Okay. So we are going to consider the rectangular solid as an illustration. The original shape is like this, has the dimension of delta x and delta z and delta y. Okay. And this is after the deformation, right? So after deformation, what happens? The delta x becomes delta x plus epsilon, delta x epsilon x, right? See, 1 plus epsilon x and 1 plus epsilon y and 1 plus epsilon z. That is an increment in the strain in the all three mutual perpendicular directions. So how are we going to write the equations like this? For the deformed body on the right hand side, for this geometry, what we are seeing here, the volume change or the volume is given by, since the change in volume itself is given as a measure here, so we directly write the volume of this deformed body, which is delta x times 1 plus epsilon x delta y into 1 plus epsilon y into delta z times 1 plus epsilon z, which can be rewritten like this. Okay. So if we recall that the strains are small, this is what we have just described in the beginning. Some of the relations what we have just seen before also, these relations are valid for a small strain. So here also we will be invoking this condition so that we can neglect the higher order terms, or the if you just consider only this first term. So then what we will get? Well, what we will get is something like this. V is approximately equal to delta x, delta y and delta z times 1 plus epsilon x plus epsilon y and epsilon z, and which can be rewritten like this, v naught into 1 plus epsilon x, epsilon y and epsilon z. So this is a kind of a definition of volumetric strain, which becomes small e is equal to capital V minus V naught divided by V naught, which is equal to epsilon x plus epsilon y plus epsilon z. Okay. So this is a volumetric strain. And what we have to remember is these relationship, they are all applied at small strains only. Okay. We are talking about elastic strain, but even there it is a small strain. So now we will focus our attention on details, how we mathematically look at this strain and or mathematically describe in terms of small equations like what we have done in stress at a point, right. So similar thing, we can just try to get a physical meaning, and this is the fixed edge on this left end, and then you have the member which is fixed from one end, and you can see that the 2 points on this member A, B, the distance between A and B is dx, and the distance between A and the fixed end is x. So this is a undeformed region or undeformed member, and this bar is just pulled in this one direction, x direction. Okay, so the what we are seeing here is the displacement, right. So the point A has moved from A to A dash, so that is displacement is u, and point B is moved here to B dash, the displacement is x plus du by dx times dx. So what does it mean? So it is not the equal displacement, that is because the here it is considered the B which is here is far away from the fixed end. So that displacement is more in B dash. So the total displacement or the distance between the A dash and B dash is equal to dx plus du by dx times dx, right. So that is how it is represented. So for that, if you look at the linear strain, here we are talking about in one direction, that is x direction here. So the linear strain is epsilon x is equal to del L by L. This is something what, in fact, even the very beginning or introduction of this course, we have just seen change in length by original length. So similar to that, it's a linear strain. Okay. So if you write it in terms of according to this geometry, what is shown here, it is A dash B dash minus AB divided by AB, and you can just substitute these measures into these equations, then what you see is du by dx. Okay. So simply what you get, the linear strain along the direction x is measured here as du by dx, that is a displacement. Okay. Displacement with respect to x direction, that is linear strain x. This is for one dimensional case, and the displacement is given by u is equal to Ex times x. So that is the displacement. To generalize this to 3 dimensions, each of these components of displacement will be linearly related to each of the 3 initial coordinates of the point. So what is that? It will be written like this. So u will have this components from Exx in the capital X direction and Exy capital, I mean this is y direction and this is from z direction. So you can also correlate this. It is almost similarly, it is quite familiar to us, right? This kind of equation we have already seen for the stress, right? Sigma xx, sigma xy, and sigma xz, right? So here it is Exx, Exy, and Exz. So what is that? It is simply the normal strain and the shear strain. So for the 3 directions or displacements in the 3 perpendicular directions and coordinates. So that is how you should look at it. So generally you can write ui is equal to Eij in xi. It's a general notation. So the coefficients relating displacements with the coordinates of the point in the body are components of the relative displacement tensors. So you can see that Exx was shown to be du by dx, and Eyy is dv by dy, and Ez is is equal to dw by dz. Okay. However, the other 6 coordinates are required for the further scrutiny. So, this is only a normal strain, right. So, it is not the complete description, the description is not ended here. So, we need further 6 coefficients which corresponds to other shear components. So, you can we can also look at this diagram which we have already seen for in fact. So, just for the completion of this derivation, I have brought it here again. So, you see that the square member has been deformed in the form of angular distortion, or I would say the deformation is angular distortion of this element here. So, what is this deformation here? The deformation is the member A, B, C, D has been deformed into A dash, B dash, C dash and D dash, and this deformation is not a linear deformation, but an angular deformation or called angular distortion. So, this the shear stress or shear strain here, it is not stress here, shear strain EYX and EXY, these are the strains we are interested. So, what is that? How do we find that? So, EXY, for example, the displacement along the x direction. So, this is what it is, EX and EY, the same nomenclature follows here, 2 subscripts. So, it is in x direction. So, DD divided by DA. So, the DD length is here, which is parallel to x, and this is DA, which will give you du by dy. Okay, that is a shear strain. Similarly, you have EYX, that will be BB, this is in y direction, and divided by AB, this distance will give you EYX, that is du dV by dx. This should be dV by dx, not there is a correction here. No, it is correct only. I'm sorry, I'm confusing here. So, we will come to that later, because we are talking about the shear strain, not the normal strain here. Yeah. So, now it will be clear here. So, we can put it all these components into the form of a matrix for a 3-dimensional strain. So, you can see that dou u by dou x and dou u by dou y and dou u by dou z, and here dou v by dou x, dou v by dou y and dou v by dou z. So, I was correct. So, we can correct this now. So, it will be dou v by dou x. So, here again Ezx, Ezy and Ezz can be given by this dou w by dou x, dou w by dou y and dou w by dou z. Similar to this, we can just if you take a 3-dimensional figure, and then it can be simply worked out like this for this. So, similar to what we have seen in the stress. So, what we have now seen so far is a linear strain, right. So, also the strain which has got 2 components. What are those 2 components? The displacement components such as EXY and YX etc. produce both shear strain and rigid body rotation, very important, right. So, we have to differentiate these 2 things, shear strain and rigid body rotation. So, look at this figure A, B, C. The one which we have just now seen, which is simply an angular distortion, but here what we are seeing is it is not a distortion here, it is simply a rotation, right, and here it is a simple shear, right, just a simple shear. So, how do we distinguish these things? So, since we need to identify that part of the displacement that results in strain, it is important to break the displacement tensor into shear contribution and rotation contribution. So, we are going to look at the displacement tensor, and we are going to break down into strain contribution and rotation contribution, like what we have seen in the stress tensor. Similarly, we will look at the displacement tensor, and also later we will also see that the strain tensor, and we will also try to decompose. So this is a notation here. Eij is equal to epsilon ij plus omega ij, where Eij is equal to half dou ui by dou xj plus dou uj by dou xi is called the strain tensor. Okay, and omega ij is equal to half into dou ui by dou xj minus dou uj by dou xi is called the rotation tensor. So this Eij can be decomposed into these strain contribution and rotation contribution. Okay, so this is very important. So in general, the displacement components such as Exy and Eyx, etc., produce both shear strain and rigid body rotation. So we can just bring in, we can just replace all this shear component and rotation component into the matrix, 3 by 3 matrix. That is here it is a shear strain matrix. So you can see that we know that how you get individual component like this and component like this. This is what we have just shown. So we can simply plug into this values, and then you will see that we will get two 3 by 3 matrix for shear strain as well as rigid body rotation for these two components. So this is just to give you an idea that these two quantities are also a tensor quantities, right? Note that epsilon ij is a symmetric tensor, since epsilon ij is equal to epsilon ji, etc. While omega ij is an anti-symmetric tensor. Please note that omega ij is equal to minus omega ji. If omega ij is equal to 0, then the deformation said to be irrotational. So very useful terminologies and relations, right? So when we say that deformation also can be linear, or it could be angular distortion involving rotation and so on, and when that can be easily represented by this rigid body rotation tensor. Okay, so this is useful. It looks it's a very simple idea, but then when you put it in a form of mathematical equation, it gives you much more clarity. So that is about the total strain. But now we talk about the definition of shear strain, which is gamma ij is equal to 2 times epsilon ij is called engineering shear strain. Okay, so we will get into the details of this and as we proceed, but let us now see what is this engineering definition of this engineering shear strain. So here it is gamma xy is equal to dou v by dou y and dou u by dou x, and gamma xz is equal to dou v by dou y plus dou w by dou z, and gamma yz is equal to dou v by dou y plus dou w by dou z. Okay, and it is not a tensor quantity. Please, that is small information. So now what we are going to do is in a complete analogy with the stress for isotropic body of the direction of the principal strains coincide with the principal stress directions. So similar to stress description where we were analyzing the principal planes and the principal stress and so on, here again the direction of principal strain and the will be considered, similar to what we have just seen for the stress. So, the element oriented along one principal strain axis will undergo a pure extension or contraction without any rotation or shear strain. The three principal strains are the roots of the cubic equation. So, what we have seen in the stress, it is the same cubic equation for the strain as well. Epsilon cube minus I1 epsilon square plus I2 epsilon minus I3, I1, I2, I3 are invariant coefficients. You can see that similar to stress, it can be written like that. So, just for the completion, I have brought this, and also to emphasize the fact that it will be a completely similar to what we have seen in stress. The directions of the principal strains are obtained from the three equations analogous to the equations of the stress. So, if you recall, we wrote a similar equations for the stress by looking at the force equilibrium. So, similar thing can be drawn for the strain as well. So, continuing the analogy between stress and strain equations, the equation for the principal shearing strains can be obtained from the equation of stress, similar to what we have written there. We can also get it from the for the strain as well. So, if you recall, all these equations exactly will match like what we have derived for the stress. So, I am just going little fast in this. Please have revise this and then it will be clear. But just for sake of time, I just want to rush it through. So, here comes the another important aspect. In general, the deformation of a solid involves a combination of volume change and change in shape. Okay. So, the volume strain or the cubical dilatation is the change in volume per unit volume. Okay. So, let us consider the volume of a rectangular parallelepiped with the edges dx, dy and dz. So, this the volume in the strained condition, it is exactly similar to what just we have developed this equation in the beginning of this class. The same equation here, the deformed body. Only the normal strains results in the volume change. Okay. So, this is another important point. Only normal strains results in the volume change. So, the volume strain delta is equal to, that is epsilon x, epsilon y and epsilon z, that is what you have seen, can be written it like this. So, and then you will get this equation, this we have already seen. So, I am just skipping that point, and this is again valid for small strains, and then we are neglecting the higher terms and so on, and then we get the delta is equal to epsilon x plus epsilon y and epsilon z. So, note that the volume strain is equal to the first variant of the strain tensor, that is delta is equal to epsilon x plus epsilon y plus epsilon z, which is again equal to epsilon 1 plus epsilon 2 and epsilon 3. We can also define similar to mean stress. Here it is a mean strain epsilon x plus epsilon y and epsilon z by 3, the mean strain or the hydrostatic component of the strain, very important. So, like we have just looked at the hydrostatic stress, and then here it is hydrostatic component of strain. So, which can be written like this as a epsilon m is equal to epsilon x plus epsilon y plus epsilon z by 3, or it is written sometimes with this notation epsilon kk, mostly in tensorial representation, which is also written as del by 3. So, the part of strain tensor which is involved in a shape change rather than volume change is called strain deviator. See, these particular terminology, right, the stress tensor which is involved in a shape change or volume change, they are very important in the deformation, theory of plasticity or metal forming and yielding theory and so on. That is exactly uh, we are emphasizing this. So, you will appreciate when we refer this term, when we looked at the theory of plasticity and deformation or any metal forming processes. So, we will refer this particular strain, which a strain deviator or a stress deviator which is responsible for the yielding process or forming process. Okay. So, that is exactly as an introduction. If you get into the, if you are familiar with these terms and the corresponding equation, then it will be easy to appreciate later without any confusion. That is why we are seeing all these things in detail. Okay. So, the strain tensor can be responsible for a shape change or a volume change. So, to obtain the deviatoric strain, we simply subtract epsilon m is a mean strain from each of the normal strain components. Okay. So, it is like this tensor matrix is exactly similar to the stress matrix. So, the deviatoric strain is epsilon ij prime is equal to mod epsilon x minus epsilon m. That means we are just simply subtracting the mean strain from the normal strain components. So, these are all normal strain components like epsilon 1, epsilon 2 and epsilon 3 something. So, if you can just expand this epsilon m and then if you rewrite this equation, this matrix will look like this. The division of the total strain tensor into deviatoric and dilatational strains is given in the tensor notation by this. So, it is epsilon ij is equal to epsilon ij prime plus epsilon m, which is equal to epsilon ij minus delta by 3 times delta ij plus delta by 3 times small delta ij. So, this is a tensorial notation. Okay. So, for example, when epsilon ij are the principal strains, I is equal to j, the strain deviators are epsilon prime 1 1 is equal to epsilon 1 1 minus epsilon m. Similarly, epsilon prime 2 2 prime is equal to epsilon 2 2 minus epsilon m. So, and so on. These strains represent elongations or contractions along the principal axis that change the shape of the body at the constant volume, very important. Okay. So, the shape change strains. And so, finally, we will just look at one more component or the topic hydrostatic or deviator components of the stress. This particular topic we did not touch. Now that we have just looked at hydrostatic component of a strain and a deviatoric strain, we will also see the similar component here. The total stress tensor can be divided into hydrostatic and mean stress tensor, which involves only pure tension or compression, and a deviator or a mean stress tensor, which represents the shear stresses in the total state of stress. Okay. In direct analogy with the situation for strain, the hydrostatic component of the stress tensor produces only elastic volume change. So, this is to be noted. So, the hydrostatic component of a stress tensor produces only elastic volume change and does not cause plastic deformation. So, we will refer exactly this particular component in the while we discussing the yield phenomenon, right. So, the stress deviator involves in shearing stresses. It is important in causing plastic deformation. So, the stress deviator we have to identify how it looks like. So, just to make it more simple, this schematic is given here. So, the total stress which involves here it is a biaxial stress with a shear strain around it, and which can be decomposed into a pure hydrostatic stress plus stress deviator. Okay. So, the hydrostatic stress is given by like this, sigma mean is equal to sigma kk, similar to epsilon kk by 3. Here it is sigma x plus sigma y plus sigma z divided by 3, and this is how it is written. So, in the tensorial notation, the decomposition of the shear stress is given by sigma ij is equal to sigma prime sigma ij prime plus 1 by 3 delta ij times sigma kk. So, you rearrange this to get the stress deviator, then it takes this form, right. So, we can now put that directly into the matrix, stress tensor matrix. So, here it is a deviatoric stress is equal to this is each the what should I say, the principal stresses are subtracted from the mean stress or hydrostatic stress component, then the matrix will look like. So, this matrix we are all familiar. So, I am just going quickly. So, it can be seen readily that the stress deviator involves shear stresses. For example, referring sigma ij to a system of principal axis. So, we can sigma 1 prime, which is equal to 2 sigma 1 minus sigma 2 minus sigma 3 divided by 3, which can be written like this, and we can rewrite this into this form. Sigma 1 prime is equal to 2 by 3 times sigma 1 minus sigma 2 by 2 plus sigma 1 minus sigma 3 by 2, which is equal to 2 by 3 into tau 3 plus tau 2. So, this is also very familiar to us, we have already seen. What is this? These are all two shear stresses, right, tau 3 and tau 2. If you recall, we have in fact shown actually the plane directions in the previous class we have shown. So, you just compare these two where these shear stresses are acting, right, exactly the sigma 3 and sigma 2 we have shown these two perpendicular, they are bisecting the two normal stresses, right, we have shown clearly in that. So, since we are already familiar with this, so it is we are able to appreciate this concept that the stress deviator involves shear stresses. So, this is very nice that it will become so handy when we discuss plasticity problems, right. So, stress deviator which involves shear stresses only this kind of stress deviator is responsible for the plastic deformation. So, that is quite obvious from this equation. So, the tau 3 and tau 2 are principal shearing stresses, we know that.